So good morning, everyone, again. So let me check. Vitor is there, right? Vitor is there. You have a different name, but you are there. Where is Eduardo? Oh, Eduardo is there. So everyone is around. Okay, guys. So good morning again. So today, I will keep on talking about some of the applications of ultrashort laser pulses, basically on micromachining and microfabrication. So just to remind you very quickly, so we know already that when we have femtosecond lasers, because of the high intensity, we are in the regime of nonlinear optics. So every time we have nonlinear optics, then we might have, for instance, multiphoton absorption. And what would be the case in this example here? That would be a 4-photon absorption process. And as I explained yesterday, since we have this multiphoton absorption, that's a nonlinear interaction. It only happens around the focal volume, which gives us a spatial confinement of the excitation. I have to finish by 10:10, and that clock is disturbing me, right? So I keep on looking at the thing. I see it's 41 already. So, okay. So we have the spatial confinement of the excitation, which we use for laser micromachining. So yesterday I showed an example of micromachining on the surface where we were able to achieve super hydrophobic surfaces. So today I'm going to try to illustrate some other applications that we can do using femtosecond laser micromachining, of course. So the first one is the synthesis of PPV. I don't know how many of you guys are familiar with PPV. So PPV is a conductive polymer. So that's the kind of polymer that people are using for this new generation of flexible devices. So that's the PPV structure right here. So it's conductive, electroluminescent, and also presents interesting nonlinear optical properties, so you can actually do photonic devices with PPV. But the thing about PPV, if you're a chemist, it's very hard to synthesize PPV in a liquid solution. And then if you wanna have a solution of PPV to print or to do a device afterwards, it's not very easy. So the way they do it is they start from a precursor polymer, this guy here, PTHT. So this is soluble. They made a film of this soluble polymer, and then you have to put it on the oven for 6 hours. And then after that, you have the conversion of PTHT to PPV. You actually break this bond right here. So that's how you do it. Okay, it works, but if you really want to do some microstructure, or if you want to do some kind of optical circuit, or even electronic circuit, that's not good, right? Because you don't have control of the spatial localization of PPV. And also, depending on what you have as a substrate, it might not resist to this thermal treatment at 300 Celsius. So one thing we can do, so that's one proposal we did some time ago, is by using femtosecond lasers. So we start from PPV or PTHT, and then with femtosecond lasers, we actually break this bond, and we create PPV. That would give us localization of, so only where, in the places where I pass the laser beam, I will promote that conversion, right? So that's more or less what I'm showing here. So the blue film is actually the precursor polymer. So that's the absorption spectrum of the precursor polymer. And then those are the lines here where I pass the laser beam, of course, in the proper conditions. Of course, we have to choose very well the velocity of the beam, which means the number of pulses and also the energy in each pulse, and the repetition rate, of course. And then in this case, you see that we have a conversion from the bluish color to the yellowish color, indicating that we are actually promoting the conversion of PVV. So if you measure the absorption spectrum of those yellow lines, that's what you get, which is exactly the expected absorption spectrum of PPV. So here's some results. So depending on the conditions you use, you might have or not the conversion from the precursor polymer to PPV. So just to give you an example, so for instance, the black and blah, blah. So if we use high repetition rate, here is where you get a better conversion, for instance, right? So the gray line here. So that's where you get the better conversion. So if you use in here, for instance, low repetition rate, So that's the gray circles there. You don't get the conversion. So what's going on there is by two-photon absorption, we are exciting the sample. Of course, it's a nonlinear absorption, but of course it generates heat afterwards. So it absorbs by two-photon, generate heats. And then of course, if I have several pulses, in the case of high repetition rate, the megahertz regime, you have an accumulation of heat which actually creates the PPV, right? So only in those points, so only here in these lines, the polymer will be conductive. So that's a very smart way, for instance, to make electronic devices using PPV, because then you have already, those lines are conductive, and the blue ones, they are dielectric, so they are isolating layers. So at once, you can make a polymer, or you can make a device. So those are sets of microcapacitors that we fabricated using the method that I just described. And here's a fluorescence microscopy image. So you can see, of course, PPV, the yellow thing, is fluorescent. So of course, you can see then it fluoresces on the green. So you can see the fluorescence, and the rest, which is actually the precursor polymer, PTHT, you don't have the fluorescence. So that's another proof that we were able actually to convert one important polymer in a localized manner. So what happens now if we go inside the volume? So here, so it's exactly the same thing, but now we are focusing the laser beam inside the volume of a given sample. And of course, the first application that everyone is doing with that is fabricating three-dimensional written waveguides. So you fabricate a waveguide inside the volume of a given surface. So, and then, of course, you can make it like three-dimensionally. That would be very interesting for complex, integrated photonic structures. So to give an example, I'm going to show the results in Gorilla Glass. So I guess everyone is familiar with Gorilla Glass, right? So that's the protective layer in our smartphones, right? So you know the layer, the glass in the smartphones is the so-called Gorilla Glass. And so it's very wide used, it's very transparent, it's mechanical resistance, that's why we use it in the cell phones. And also is integrated with electronics, right, in the cell phones. But of course, it would be very nice if we were able to fabricate waveguides in Gorilla Glass in such a way that we can integrate electronics and photonics in the same platform, in the same type of glass. So in this case, just to give you an idea, we are using a 1 kilohertz laser. So it depends now. Depending on the glass, you might go with the megahertz, but the megahertz, it has a smaller energy per pulse. The point is, because it's a Gorilla Glass, if you try to micromachine only using nanojoules of energy, it doesn't work. So you need microjoules because it's very resistant, the glass. So that's why we use the femtosecond laser with the kilohertz. So those are some lines we fabricate in Gorilla Glass just to illustrate. And the minimum, the threshold energy that we need to fabricate on Gorilla Glass is on the order of 500 nanojoules, so half of a microjoule, okay? So that's a waveguide written in Gorilla Glass. There's a top view optical microscopy. In fact, that's a 15 millimeters long waveguide. Of course, it's just a take of it, and it's 100 microns below the surface, right? So that's not on the surface of the glass. That's actually below the surface. So here you can see it. So that's the output or the exit of the waveguide, and then we can couple light in this waveguide. So we place it in this coupling system here, where I'm coupling a Hini laser, and then on the other side, I see the light coming out from this three-dimensionally written waveguide inside a piece of glass. Gorilla Glass. So people haven't studied much about the nonlinearities of Gorilla Glass, but we actually did in our lab. So it presents a reasonable N2. So it presents a reasonable Chi3 effect. So when we couple, instead of coupling a Hini laser in the Gorilla Glass, if we couple a femtosecond laser in Gorilla Glass, the nonlinearity is high enough that on the other end, in the output, you can get white light continuum generation. So we can get white light coming out from the Gorilla Glass waveguide. So that's what you see here. So that's the spectrum. So you see you barely see the gray line. So the gray line here, I'm just indicating, it is the spectrum of the pump laser. And then, because of one effect that is related to self-phase modulation, in the output, you get a very broad band. So you see here, it comes from 800 all the way to 500 nanometer, and I'm actually have a filter to block some part of the light in this part here. But anyways, so it goes from 500 all the way to 800 nanometers. It gives this kind of white color coming out. So we can use it for photonic devices, or even if you need to have, for some reason, white light generation in this case. To give another idea, so this is threonine crystals, so amino acids. So amino acid crystals, they are good because you can eat them, right? And then you get stronger. That's what people say. But I mean, first, the growth of those crystals is relatively simple. They are not very expensive, and they present very high optical nonlinearities, second-order nonlinearities. So, for instance, if by any chance, so as many of you guys are interested in bio applications, so it's totally biocompatible, right? So if you need a platform for some bio applications, so amino acids a good one, and it presents interesting nonlinearities. So that's the transparency, so that's the index of refraction, just some details for the design of optical devices. But the thing about, so why don't we actually fabricate a waveguide in this amino acid, threonine, and since it has a high chi2, why don't we get guided second harmonic generation? That would be the idea, right? So it would be nice, like having a device where you have a guided second harmonic generation. Okay, that might work. However, when you try to just do in the way I did with the Gorilla Glass, if you just pass the laser through in order to densify the material, in order to get guiding by increasing the index of refraction, it doesn't work for such crystals. So in fact, for the amino acid, when in the position where you pass the laser beam, the index of refraction actually decreases instead of increasing. So the only way to fabricate a waveguide in such type of material is by fabricating what we call cladding waveguides. So instead of fabricating, so it's much more work, because in the other case, it's basically I make one pass, the index of refraction increases, and I have a waveguide. So in this case, what I'm doing is I'm doing several passages like this. So in each of this region, the index of refraction is smaller. So in the center, the index of refraction is higher because it's the index of refraction of the material itself. And then all around it, where the index of refraction decreases, the index of refraction decreases, and then I have guiding in the center. So that's what we call a cladding waveguide. So the good thing about a cladding waveguide is that for sure, in the central portion where you are going to guide the light, you are not changing the material whatsoever, right? Because in the Gorilla Glass, you can argue, okay, you are passing the laser, you are increasing the index of refraction, but you might be changing the material also, right? So that might not be the original Gorilla Glass. So that might be something different. That's not the case here. So that's a good approach where you want to maintain the properties of the material, which is exactly the case for second harmonic generation. So just going, on the other hand, you don't get a very nice profile of guiding, right? So, okay, but it's still okay. It's guiding light. You can engineer that a little if you wish. You can do some modeling and maybe try to find a better way to write this waveguide. But okay, it's still guiding. And then a couple femtosecond laser light at 800 nanometers, 7 something here, 750 more or less. So that's the pump beam spectrum. And then I guided that, I coupled that light in the waveguide. So that's the output of the waveguide. You see, it's even worse. So it depends a little bit on how you do the coupling. So sometimes the profile is even worse. And then you get blue light coming out. So you see 375 nanometers. So that's the spectrum of the light that's coming out from your waveguide. So that's second harmonic generation. So that's exactly half of the wavelength. If you measure the intensity of the second harmonic light as a function of the input power for the for the fundamental beam, you get a parabolic line, a squared line, which again proves that you are fabricating second harmonic generating cladding waveguide. So that's laser micromachining, like in 2 examples, right? Maybe 3. So you can write waveguides, you can write 3-dimensional waveguides, or you can write cladding waveguides or this kind of application. There's another method that we use in our lab, which is the laser-induced forward transfer. So in this case, we have a donor material. We focus the laser beam in this donor material, which is a film, and then we expel this material to a receiver one, to another substrate. So that's called laser-induced forward transfer, right? So we transfer this material to the other one. It's basically like a laser printing. So in this case, I'm just going to show results for chalcogenides. So chalcogenides are interesting materials, mostly for applications, telecom applications in the infrared. So they are transparent up to, let's say, 5 microns, 4 microns. So here, just to give you an illustration, so that's the material being transferred. So by using 20 nanojoules of energy, those are atomic force microscopy images. So you see that's the region where we actually transfer the material. And I play with the conditions. We can get this kind of periodic structures during the transfer. And each of those pillars or semi-spheres here, they are about 200 nanometers. So by using laser light at 800, focusing in, let's say, 1 micron or so, depending on the condition or controlling the condition, we can make those lines and we can actually transfer periodic structures. So we are actually aiming for some photonic crystals using this method here. So the third, so that's everything I want to say about laser-induced forward transfer. So the last method is the femtosecond laser microfabrication, in which we use femtosecond lasers and nonlinear optical phenomena to fabricate 3-dimensional structures. So that's a SEM image of this microstructure there. SEM stands for scanning electron microscopy. So how does it work? So basically, you have a monomer, which is basically a viscous liquid, right? And then you have a photoinitiator, which is a small molecule that, when excited, generate radicals, which induce the polymerization reaction, right? So you react those monomers, creating a polymer. So you go for a viscous liquid to a solid thing. So that's polymerization. The only thing is this photoinitiator here, instead of using that, so in chemistry, there are chemical photoinitiators. You just put it there, there's some chemistry going on, and then you generate the radicals, and then you get the polymerization. Some of them, they are thermally generated. So you put the photoinitiator, you heat it up, it creates the radicals, and then you go. Some other ones, they are photoinitiators, right, in which you need light. So, but in this case, instead of using just 1 photon absorption light, we are going to use 2 photon absorption to excite this photoinitiator, breaking creating the radicals to do the polymerization. So as we know already, so I need 2 photons to go from the ground state to the excited state of the photoinitiator in order to break the molecule, in order to do the polymerization. But of course, because it's a 2-photon absorption process, the absorption of the photoinitiator is 2 photons, it only occurs around the focal volume. So basically, only in this region, the intensity will be high enough to induce 2-photon absorption and then to induce the polymerization. The setup is something like this. So we have the laser, shutters, scanning mirrors to move the beam X and Y, and the sample actually is placed in a stage that I move the Z direction. So I move X, Y, and Z, and then I can fabricate 3-dimensional microstructures. I'm going to skip this. I'm running out of time already. So the way it works is basically I scan the beam, I scan the beam, there you go, right? And then it polymerizes, and then I do the next layer, so on and so forth. That's an illustration of how it works. That's in real life. So that's a camera in our setup. Okay. I hope it works. There you go. So you see I'm passing the laser beam. It's solidifying the material, so it changes the index of refraction. And then I made the second layer. That's only 2 layers. So that's a real-time fabrication. The structure here is 30 microns by 30 microns by 12 microns tall. Right? And then after I do the fabrication, I just remove, right, the unpolymerized resin, and then I have the 2-photon microstructures fabricated on top of a glass substrate, for instance. So that's a Christ we fabricated a few years ago, just to illustrate, no religions aspects related, because, you know, that reminds of Brazil somehow. Okay, I stopped there. I guess nowadays, in order to remind Brazil, we would have like presidents on jail, right? That's another way to remind of Brazil, I guess. But, alrighty, Christ is there. We can also fabricate sets of microstructures and with whatever with whatever shape you have in mind. So one application of I'm gonna now try to illustrate some applications of it. So there's a microring resonator fabricated using two-photon polymerization. Of course, as you see here, the surface is much smoother than other surfaces because, of course, we are looking for smooth surfaces since we want to do a microresonator. And, of course, we will have a resonator like this. So the idea is having high Q factors in order, of course, to use that for confinement of radiation or for sensor applications. So here, just to give you an idea, so that's one of our resonators. So people are doing that in silicon photonics a lot, right? So if you look in silicon photonics, people use standard lithography, and then they might fabricate good, very good, actually, microresonators. But that's in silicon photonics, right? If you need, how would you dope that thing? So if you want to have, so in those devices, you rely on the nonlinearity or on the optical properties of silicon, and that's it, right? But in here, since it's a polymer, it's an organic thing, you can dope, you can add other materials in order to get functionalities for those resonators. Okay, what I want to show here, that's the surface, and you see the roughness we are getting is on the order of 2 nanometers. And then we couple light, so we have a tapered fiber, optical fiber. We approach the fiber from our resonator, and then we couple light, and then we see the resonance spectrums, the resonance spectrum of those resonators. We can actually analyze each of those modes, and so on and so forth. So we can do it for applications. So if you are wondering about the Q factor, so the Q factor, the quality factor of our resonators is on the order of 10 to the 5th, which, of course, it's maybe 10 times smaller than what you can get with regular silicon photonics. But in here, we have a polymer. And, of course, polymer, it does have absorption in the near infrared, right? So here, that's the state of the art. You're not going to be able to decrease it. If you do a polymeric thing, you're not going to be able to get anything smaller than this. But it's competitive with whatever you have in the literature, more or less. Of course, you can dope, as I mentioned before. We can have now in our polymer rhodamine B, which is a fluorescent polymer. And in this case, we can excite our microstructure with a Q-switched mode-lock laser, as I mentioned before, in the green. So I have here my microstructure. I use this laser to excite the microstructure containing the rhodamine B, and then with an optical fiber, I can collect the emission, and then you see laser emission. So those are the modes of our structures, right? So, so that's the free spectral range here. So those are the modes of our structure. If we just only focus here on those 4 different excitation intensities, then here, if you look at the intensity of those peaks as a function of the excitation intensity, you get the threshold curve which is expected for laser action. So we were actually able to fabricate micro-ring lasers using two-photon polymerization. Okay, I was running to get to this part of the talk. Since that's a biophotonics school, now in 5 minutes I will talk about my bio applications, right? Okay, of course, that's a method that you can use to fabricate micro things, right? And then that's kind of in the right scale for cells and bacteria, right? So one idea would be using two-photon polymerization as a way to produce scaffolds to study the growth or the development or developing of cells and bacteria, as I mentioned before. So one example then. This is what people call, that's a microscaffold. So that's a wood pile structure. So in this case, I was fabricating something like this. So some lines and then crossed lines, so on and so forth. So in the end of the day, by controlling the movement of my beam, I can control how big is the porous of this structure. And this structure is totally connected. So if you leave one bacteria here, it can go anywhere because it's completely connected, right? There is no dead ends. So if we fabricate it with different porous size, and porous size means this, the distance here, so 100 all the way to 12 microns. And then the idea was to study how fibroblasts develop in this three-dimensional arrangement. So those are fibrosarcoma cells, fibroblasts. So you see, after some treatment, it's really biocompatible. So if you seed the cells around, they develop in the microstructure, they seems to enjoy the microstructure. And then, of course, those cells, they are, how is that? I forgot the word. I'm not that good in bio things. They have GFP, but they are, how is that, people? How do you say that? The GFP is in the genome of the cell, right? So it's not doping the cell. Transfected, thank you very much. Yeah, so the cells are transfected with GFP, right? So it's not only that I'm dying the cells, right? So it has that in the genome. So that's a way we can use confocal microscopy to actually see the cells moving around and actually even in 3D. So that's a movie. So that's for the 100 microns. So you always seed the cells around, and then you see that in this case, they only stay around the central part of the edges of the structure. So now, if we go for the 12 microns, again, you seed the cells around, and of course, they don't enter inside the microstructure. And then, of course, if you do something like this, which is 50 microns, you seed around, and then you have a better, a more homogeneous distribution of the cells on your scaffold. Of course, since we have a confocal microscopy image, you can, of course, get the 3D movement of the cells, and then you can, for instance, analyze the velocity of the cells and for how long they stay still in a given position, and then you can compare that with data that you get in 2D, which would be interesting for tissue engineering. We can also make structures in which we have one part of the structure containing a given dopant and another part with another dopant. For instance, you would have something here which is a growth factor for bacteria or for cells. And then you can direct the growth of cells. So in this case, we did something on the other way, in which only the central structure contains ciprofloxacin, which is an antibiotic. And then we seed here Escherichia coli, E. coli, and then, of course, you don't have the E. coli developing in this part of the structure. And then, of course, you can analyze the density of the structure in this microenvironment. So you can actually do biology in microenvironment. So instead of using, like, how is that, plates? Petri dishes. Petri dishes, and do that, like counting colonies, this kind of stuff. You can actually do that with just a couple of cells or bacteria. And then, since in the optics group here, they do traps of atoms. So we decided to do traps of bacteria, right? So we have like a little door, then the bacteria can enter, and they stay there, and then we can count how long does it stay inside, and how long does it take to get inside. So I call that bacteria trap, which sounds good, I think. But then my students, they call that bacteria curral, right? Curral de bactéria, né? Which I don't think sounds that good. Anyways, so here just an example. So you can count the number of bacteria you have as a function of time, and then you can do some studies on this kind of bacteria. Since I know you're not going to visit our lab, so like a 2 minutes virtual lab tour. So that's our picosecond laser lab, where we do some spectroscopy, and also the excitation of our microring resonators. That's our femtosecond laser, where we have 150 femtosecond laser that's used for pumping probe experiments, that's used for nonlinear spectroscopy, nonlinear absorption, multiphoton absorption measurements, as well as some, depending on the energy you need, that's also for some part of the microstructure. That's our dragon laser. That's a 30 femtosecond laser. That's the one we also use for the lab nowadays is a little different, so it's a little bigger than this. So that's an old picture. But that's the laser we also use for laser pulse shaping and other spectroscopies. That's our oscillator, 20 femtosecond oscillators that we use again for micromachining, two-photon polymerization. And that's the other femtosecond laser. That's a 50 femtosecond, 5 megahertz repetition rate that we use for lift in this corner and micromachining on the other one. So bunch of the work I just flashed here is being done by several of my students and postdocs and people that come into the lab and work. That's it. I have to acknowledge FAPESP, NPQ, and CAPES from Brazil, and US Army and US Air Force for the funding of my research. And again, thank you all for your attention. Again, you go to Google, and you find the presentation link. And I made sure that both presentations are there already, so you can just go and upload, download, right, if you wish. OK, guys, I guess that's it. And thank you for your attention. That was fast. That was ultra fast, right? Seriously. So can I take a few questions? Maybe one?
I guess maybe just one.
Maybe one question, or curiosity, or whatever. And then, OK. We have the guy there. Since we're here, you can talk to me later, right?
Yeah, just one very quick question. We are running on time.
Thank you very much. It was a beautiful presentation. I'm very curious about the dispersion profile of the Gorilla Glass, because I see you use it in supercontinuum generation. And the dispersion profile will determine the type of nonlinear, whether it is soliton-based or cell-phase modulation. So I want to know the dispersion profile of it.
That's a very, you work in the area. So it's not soliton, it's cell-phase modulation. So we actually measured the index of refraction of Gorilla Glass in some wavelengths. And then I'm not showing any results of the N2 characterization or any spectroscopy data in this talk, but we did it. I skip it, otherwise I wouldn't have time. But in our modeling of the nonlinearity, we include the dispersion, but that's a cell-phase modulation base. It's not soliton base, unfortunately. Well, it depends, right? So thank you. That's
OK, so thank you very much again, Cleber.